When most people hear software testing, they probably picture someone just clicking around, trying to break an app, right? But what if I told you it's actually this deep, critical engineering discipline? It's really the unseen science that stands between a smooth digital experience and, well, absolute catastrophe. So today, let's dive into the super high stakes world of software testing.
Okay, so let's start with a crazy story. Picture this. June 4th, 1996, the Ariane 5 rocket, a massive piece of engineering carrying $1 billion worth of satellites, suddenly veers off course and self-destructs just 37 seconds after launch. An unbelievable, incredibly expensive failure. And you're probably thinking, okay, a rocket. What on earth does that have to do with software testing? Well, you're about to find out.
All right, now let's jump to something a bit more recent, something you might actually remember. The huge, massive launch of Disney Plus. For literally thousands of super excited users, it was just a day of error messages and total frustration. I mean, they had the whole world watching, and the system just stumbled. So we've got a rocket exploding and a streaming service crashing. And believe it or not, these two disasters are connected by the exact same hidden force.
Now, to be fair, the team at Disney wasn't totally unprepared. I mean, they knew launch date was going to be absolutely massive. So they stress tested their systems for a mind-boggling number of people streaming videos all at once. And on the surface, that makes total sense, doesn't it? That seems like the most obvious thing to worry about, the biggest bottleneck.
But here's the thing. Here's the twist. The system didn't crash because everyone was streaming The Mandalorian at the same time. Nope. It crashed because of everyone trying to create an account, log in, and just browse the library before they could even hit play. Think about that. They tested for the right amount of traffic, but they aimed it at the wrong part of the system. And this, right here, shows that effective testing isn't just about breaking things. It is all about strategy. So the big question is, how do we stop these kinds of massive failures from happening? Well, luckily, the entire field of software engineering has developed this set of core principles, almost like a philosophy, to guide how we even think about testing. So let's walk through what I call the 7 foundational rules. Okay, principle number 1. And honestly, if you only remember one thing from this, make it this one. Testing shows the presence of defects, not their absence. So let me ask you this. If you run 1,000 tests and every single one passes, is your code perfect? No, absolutely not. All it proves is that you haven't found a bug with those specific tests. Think back to that Ariane 5 rocket. Guess what? It passed all of its pre-flight software tests. See, testing can only prove that defects exist. It can never, ever, ever prove that they're not there. So you might be thinking, well, why can't we just test for everything? And that brings us right to principle number 2. Exhaustive testing is completely impossible. I mean, look at this number, 72 billion. That's how many test cases you'd need for just a simple function with only a few inputs, something like an age range and a date. Why so many? Because every single possible combination of inputs creates a brand new test case. Trying to test all of them isn't just hard, it's computationally insane. It's just not possible. We have to be smarter about it. Which leads us to a really crucial point. You can't just wait until the end and then tack on some testing. No, it has to be baked into the process from day one. Why? Well, think of it like this. Finding a bug during the design phase is like spotting a mistake on a blueprint and fixing it with an eraser. Easy. But finding that exact same bug after the software is already built and out in the wild, that's like performing open heart surgery. It's way more expensive, way more risky, and a whole lot harder. So principle 3 is to start testing early. You get that feedback when it's cheapest and easiest to do something about it. All right, here's a really fascinating pattern that experienced testers have noticed over the years. Bugs, they don't spread out evenly through the code. They tend to clump together in very specific areas. We call this defect clustering, and it follows the classic 80-20 rule. You'll find that about 80% of the problems are hiding in just 20% of the code. So smart testers use this as a guide, right? They focus their energy on those hot spots, the really complex parts of the code or the bits that are always changing. That's where the bugs love to hide. Okay, moving on to principle number 5, which we call the pesticide paradox. This is a great analogy. Imagine you're a farmer and you spray your crops with the same pesticide over and over again. What happens? Well, eventually the bugs evolve, they become resistant, and the pesticide stops working. Software tests are exactly the same. If you keep running the exact same suite of tests again and again on a program that's constantly changing, they'll eventually stop finding new bugs. This paradox means we have to constantly be updating and varying our tests to keep them fresh and effective. Now, this next one might sound kind of obvious, but it is so critical. Principle 6, testing is context dependent. Think about it. You would never test the software for a heart pacemaker the same way you test a food delivery app, right? For the pacemaker, reliability is literally a matter of life and death. Failure is not an option. But for the delivery app, a small visual glitch is annoying, sure, but it's not a catastrophe. The context, what the software does, and what happens if it fails, dictates absolutely everything about your testing strategy. And for our last principle, number 7, we have to look at two very different but equally important questions. The first is verification. This is basically asking, are we building the software right? Do we follow the blueprint? Does it mean all the technical specifications? But then there's validation, which asks a much deeper, more important question, are we building the right software? Does this thing we built actually solve a real problem for our users? You can have a piece of software that is perfectly verified. It checks all the boxes on the spec sheet, but it completely fails validation because, well, nobody actually wants or needs it. Okay, so now we've got our guiding philosophy, these 7 big rules. That's the why. But how do we actually put this stuff into practice? How do we do it? Since we know that testing everything is impossible, we need smart, strategic techniques that help us find the most bugs with the least amount of effort. So now we're going to move from theory into actual technique. So the challenge is pretty clear, right? On one side, you've got this impossible dream of exhaustive testing, trying every single input. And on the other, you have the smart reality, using what we call heuristics. These are basically rules of thumb, clever shortcuts that let us strategically pick a small but really powerful set of tests. So let's look at a couple of the most important techniques that engineers use every day. First up, we have a technique called equivalence partitioning. The core idea here is actually pretty simple. You divide all the possible inputs into groups, or partitions, where the software should treat everything in that group the same way. For example, if your system is supposed to handle ages 18 to 65 as adult, why would you waste time testing age 18 and 19 and 20 and so on? It's pointless. You just pick one number from that group, say 35, and if that works, you can be pretty confident that all the other numbers in that group will work too. It's a huge time saver. Now, building right on top of that idea is something called boundary value analysis. And this technique is, frankly, brilliant. Why? Because years of experience have shown us that a massive number of bugs happen right at the edges, the boundaries of an input range. So if a text field accepts numbers from, say, 2 to 17, you don't bother testing a safe number in the middle like 10. No, you focus on the edges. You test the minimum, 2, the maximum, 17, and then crucially, you test what's right next to them, just inside, so 3 and 16, and just outside, 1 and 18. That's where the code is most likely to break. So these kinds of techniques, they're not just used at one single point in time. They're applied all across the entire software development lifecycle. You have to remember, testing isn't just one big phase at the end. It's really a series of stages that go from the tiniest piece of code all the way up to the finished product in a customer's hands. From a high level, you can kind of think of it as a journey in 3 big steps. First, you have development testing. That's where developers are testing their own code as they're building it. Next comes release testing, where a totally separate team takes a complete version of the software and really puts it through its paces before it can go out the door. And finally, you have user testing, where real users get their hands on it and test it in their own real-world environments. So let's zoom in on that first step for a second, on development testing. It's actually made up of different layers, and we often picture it as a pyramid. Right at the very bottom, the foundation, you have unit tests. This is where a developer tests one single tiny function completely on its own. Then you move up a level to component testing. Here, you take a few of those units, stick them together, and see if they play nicely. And then at the very top, you have system testing, which checks that all the big, major components of the whole application work together just like they would in the real world. And then what about that final stage, user testing? This is, you could say, where the rubber really meets the road. It usually happens in 2 phases. First, there's alpha testing. That's when you invite a small group of friendly users to the developer's site, to your office, and watch them use the software. Then, once you've ironed out those initial kinks, you move to beta testing. That's when you release the software to a much wider group of people out in the public and let them experiment with it in the true chaos of their own real-world setups. Okay, get ready for a concept that I promise you is going to sound completely insane at first. What if I told you that some companies deliberately test and even break their live systems, the ones that your actual customers are using right this second?
It sounds crazy, but this is the absolute frontier of building truly resilient systems.
This practice has a name. It's called chaos engineering. And no, it's not about just creating random chaos for fun. It is a highly disciplined, controlled experiment. You're basically asking a tough question. If one of our servers suddenly fails at 3 a.m., will our system recover automatically without any of our users even noticing? And really, the only way to know the answer for sure is to try it. And the most famous example of this in the entire world is Netflix's Chaos Monkey. It's a real tool that runs inside their live production network and just randomly terminates servers. It just shuts them down. The goal for the Netflix engineering team is to build a system so tough, so resilient, that this monkey can do its absolute worst, and their most important metric, what they call stream starts per second, doesn't even flinch. It's all about finding those weaknesses before they can turn into a real catastrophic outage. And this brings us full circle, all the way back to our very first principle. If we accept that testing can never, ever prove a system is perfect, then what's the point? What are we even doing? Well, the point isn't perfection. It's confidence. Every single test you run, every bug you find, every potential failure you plan for, it's all an investment. It's an investment in building confidence. Confidence that your system will do what it's supposed to do, confidence that it can handle the chaos of the real world, and most importantly, confidence that it will actually serve its users and serve them well.